In the last screencast, we discussed three representations of functions. The first was a flow diagram, the second was input-output tables, and the third was an equation. In this screencast, we look at the fourth way functions are commonly represented, and that is by a graph. The graph of a function displays the input-output pairs for a function, and it does it on a coordinate plane. Each input-output pair is expressed as a coordinate pair, namely input, output. And each of those input-output pairs then is represented by a point on the plane. Consequently, the horizontal axis generally corresponds to the inputs, while the vertical axis corresponds to the outputs. Let's draw a picture of this so you can see what I'm talking about. So I'm drawing the coordinate axes right here. When we're talking about the graph of a function, remember there are two variables, the input variable and the output variable. We put the input variable on the horizontal axis and the output variable on the vertical axis. So let's suppose that I took a particular number and I put it into this function. I find that number on the input axis. Maybe it's this number right there that I'm marking in blue. That's the number I'm putting into my function. Suppose we put that number into our function and we got out this number, the number I'm marking here in blue on the output axis. So these two numbers represent an input-output pair for this function, and for a graph we look at the intersection of this input and this output, and that gives us a point right there. That point has coordinates input, output. So the graph of a function displays not just one input-output pair like this one, it displays all input-output pairs for a function. So just recall, when we're talking about a function and its graph, all of the points that are graphed are input-output pairs for that function. The horizontal axis always shows the inputs, the vertical axis always shows the outputs, and consequently the coordinate pairs always go in the order input, output. Let's try this out on an example. So in example 4.2, we're looking at the function given by the equation y equals x squared minus 4. You can see that the letter x is playing the role of the input. We're squaring x and then subtracting 4. The output is given by the letter y. Let's start by making an input-output table for this function. Notice that I have the first column representing the inputs or the letter x, and the outputs are in the second column given by the letter y, and in the third column I have the xy pairs or the input-output pairs. So let's substitute -4 into this function. We take -4 and we square it. That gives us 16. 16 take away 4 is 12. So we have an output of 12. The coordinate pair is the same as the input-output pair. So the input goes first and the output comes second. So input, output. Now let's substitute -3 into the function. -3 squared is 9. 9 take away 4 is 5. So we have an output of 5. The input-output pair is -3, 5. That's the coordinate pair that we would plot on the graph. Continuing on, if we plug -2 into the function, we arrive at 4. Take away 4 gives us 0, so the output is 0. and the coordinate pair is -2, 0. If we continue on substituting in the remaining inputs, we arrive at, let's see, -1 squared is 1. 1 minus 4 is -3. If I substitute 0 in, I get -4 coming out. If I put 1 in, I get -3 coming out. If I put 2 in, I get 0 for an output. If I put 3 in, I arrive at an output of 5. If I put 4 in, I arrive at an output of 12. So the remaining input-output pairs are -1, -3, 0, -4, 1, -3, 2, 0, 3, 5, and 4, 12. So these coordinate pairs here are ready to be plotted on a coordinate axis system like the one shown here. On the next page, I have a set of axes ready for us to plot these points. Okay, let's go ahead and plot these input-output pairs on the axes shown in this picture. First of all, notice that the horizontal axis corresponds to the inputs of our function, and the letter X is representing the inputs. The vertical axis represents the outputs of the function, and the letter Y is representing the outputs. So let's go ahead and plot these input-output pairs. Let's see, one of the pairs was -4, 12. So I look to -4 on the x-axis and 12 on the y-axis, and then I mark the intersection with a point. Next one is -3, 5. So -3, 5 is about right here. I may not be able to draw these points quite as accurately as you're able to, but I think you'll get the point. -2, 0. That's right here. -1, -3. That is right about there. 0, -4. It's right at that location. 1, -3. 2, 0. 3, 5. And 4, 12. The scatter plot that you have just drawn above is not the full graph of the function. First of all, a scatter plot is simply a plot that just shows isolated points like this, points that are separated from each other. That's a scatter plot. This scatter plot is not the full graph of this function. The points that we plotted, there were 9 of them. They corresponded to 9 input values that we chose. Namely, we chose values between -4 and 4, and they were all integers. But there are many other numbers that we could have chosen to put into this function. For example, we could have put the number 3.5 into this function, or -1.6, or we could have put the number pi into this function, or the square root of 2, or 2/3. There are many other numbers that we could have put into the function that we didn't. each one of those numbers would yield another point on this picture. To draw the full graph, we would need to continue plotting points for every possible input value. However, from the points you've plotted above, these 9 points, you can see a pattern or a trend that should enable you to predict what the full graph looks like. The picture below shows the completed portion of the graph between x equals 4 and x equals negative 4. So right here is x equals negative 4. This is x equals 4. And you are viewing the portion of the graph between these two input values. And you can see that the graph is a curve. Functions that have a single input variable, like x, will yield curves in the plane, as long as the value of the input variable is free to be any real number. Okay, now let's talk about the intercepts of a graph. The intercepts of a graph are the places where a graph passes through an axis. If we look at the picture above, the graph passes the x-axis in 2 spots. It crosses the x-axis at x equals 2, and it crosses the x-axis at x equals negative 2. Those are the x-intercepts, or also called horizontal intercepts. The graph also intersects the y-axis right here at negative 4, at y equals negative 4. Negative 4, or y equals negative 4, is referred to as the y-intercept, or the vertical intercept of this function. Before moving on, let's take a little bit more time and talk about how to find intercepts. In this course, you will commonly be asked to determine the intercepts of a function algebraically. So let's look at the graph above here. Let's just take this point right here, or this intercept right here. If we imagine what the coordinates of that point are, you can see that the input value is 2 and the output value is 0. So the coordinate pair is 2, 0. So the 2 is the x-intercept, and notice the output value is 0. Now let's look at the other x-intercept, x equals negative 2. If we look at the coordinates of that point, the input is negative 2 and the output is 0. So once again, the output value is 0. There's a lesson to be learned here. If you want to calculate the x-intercepts, or the horizontal intercepts of a function, you have to look at the input values that cause the function to have an output of 0. In other words, to find x-intercepts, you set your output equal to 0. So I'm going to summarize that here. So for x-intercepts, for an x-intercept, you have to set your output equal to 0. Okay, now let's talk about the y-intercept, negative 4. If we write down the coordinates of that point, the second coordinate is negative 4. The first coordinate is a 0. Remember that the coordinates go input, comma, output. So this 0 is an input value, and the negative 4 is an output value. In order to find a y-intercept or a vertical intercept, what we have to do is determine the output value when the input is 0. In other words, to find a y-intercept, we have to set our input equal to 0 and then determine what the output is. The following 3 examples will give you some practice working with intercepts. Go ahead and pause the recording right now and work these 3 examples. Then continue playing the recording to see the examples fully worked out. Okay, let's go ahead and work example 4.3. Sketch a graph of a function that has a vertical intercept at -3 and exactly 3 horizontal intercepts at -2, 1, and 4. So I'm going to begin by drawing a coordinate axis. Now this is the graph of a function, which means that the horizontal axis represents the input values of this function, and the vertical axis represents the output values of this function. I'm also going to draw in a few tick marks. That's 1, 2, 3, 4, 5, -1, -2, -3, -4, -1, -2, -3, and 1, 2. That should be enough. Okay, this function has a vertical intercept at -3. That means the graph of this function crosses the vertical axis at -3 at this point right here. The function also has 3 horizontal intercepts at -2, 1, and 4. So the graph has to cross the horizontal axis in those 3 places and only those 3 places. Recall that the graph of a function is a curve. So we have to draw a curve that passes through these 4 points. There's more than one curve you could draw here. So I'm going to just draw one that will work. I'm going to have it come up, go down like this, go back up, and come back down. And I'm going to have my graph just continue going back up like that. So this curve passes through the horizontal axis in only 3 places, and it passes through the vertical axis in just 1 place. You could have drawn something that was a little bit different. Now let's look at example 4.4. Determine the horizontal and vertical intercepts for the function given by the equation y equals 4t minus 16. First of all, let's make sure we understand what this function is doing. The letter t represents the input for this function. 4 times t minus 16 gives us the output, which is represented by the letter y. So if I take a number and I put it into this function, I'm putting it in the location where t is. So if I take a number and I put it in, the first thing that will happen to that number is it gets multiplied by 4. The second thing that happens is 16 gets subtracted, and then the result or the output is given by the letter y. If we were to consider what the graph of this function might look like, we would begin by drawing the axes like this. Now, in this particular case, the horizontal axis represents the input and therefore would be represented by the letter t. The vertical axis represents the outputs, and they are represented by the letter Y. So in this particular case, the horizontal intercepts will be t values because it represents values that are on the t-axis. Vertical intercepts are going to be particular values of y in this case. So let's go ahead and begin by trying to calculate the horizontal intercepts of this function. So we're going to start with the horizontal intercepts. From the previous page, we learned that to find the horizontal intercepts, you have to set the output equal to 0. In this case, that means we have to set y equal to 0. If I take the equation and I replace y with 0, I arrive at the equation 4t minus 16 equals 0. The horizontal intercept will be the value of t that satisfies this equation. So let's think. 4 times some number t minus 16 equals 0. Can you think of what t must equal? If you think about it briefly, you would arrive at the conclusion that t must equal 4. So t equals 4 is the horizontal intercept of this function. In other words, if we were to draw the graph of this function, the graph would pass through the point 4, 0 on the plane. Now let's look at the vertical intercept. To determine a vertical intercept, we have to set the input equal to 0. In this case, that means we set t equal to 0. If I replace t with 0 in the equation, I arrive at y equals 4 times 0 minus 16. If I work that out, I arrive at negative 16. So y equals negative 16 is the vertical intercept. In other words, if we were to draw the graph of this function, the graph would pass through the point 0, negative 16 on the plane. Now let's look at example 4.5. To answer the two questions in this example, you have to go back and think about the primary feature of a function, and that is that every input has at most one output. Now let's take that thinking and apply it to question B first. Can the graph of a function have multiple vertical intercepts? Well, recall that a vertical intercept is the output value when you put the number 0 into the function. So let's think. Suppose we put the number 0 into the function. Is it possible that we could get multiple outputs? The answer is no, because every input has at most one output. So if I put the number 0 into the function, I can get at most one number. Therefore, I cannot have multiple vertical intercepts. So the answer to this question is no. Now let's look at question A. Can the graph of a function have multiple horizontal intercepts? Well, a horizontal intercept is an input value that causes the output to equal 0. So if I ask whether a function can have multiple horizontal intercepts, I'm asking, is it possible for a function to have more than one input that causes an output of 0? can more than one input give an output of 0? In this case, the answer is yes. For example, if I look at the graph that we drew above, this function has 1, 2, 3 horizontal intercepts. In other words, if I take the values -2, 1, and 4 and I substitute them into the function, I get the value 0 as an output every single time. So I have 3 values which when I put them into the function all yield 0, and there's no problem with that.